No, we have to find the antiderivative before we go to a triangle. U sub? Take out a sine. Good, that's it. You take out a sine theta. See, so you're thinking, look, if U substitution, just a basic U substitution, if I choose U to be sine, the derivative is down in the bottom. I don't want that. If I choose U to be cosine, the derivative is up here, but it's sine cubed, not just sine. But you can peel off one sine up on top, can't you? So I'm going to peel off one of the sines, like this. Okay, I'm going to peel off one of the sines off the top. And then, if I'm going to do that, my U's got to be what here? Cosine. The derivative of that will be negative sine U, or sine theta d theta. Negative du sine theta d theta. And so that should take care of it, but I need to get everything in here in terms of U. So this cosine is going to be U squared. That'll be negative du. The sine squared? 1 minus cosine squared. Rewrite it. Almost there. Almost there. Oh no, because then we got to take it all back, don't we? Just have to do all that. So, all righty. Let's rewrite the integral. 3/16 integral. What do we have up top there? Or what do we have? 1 minus U squared. It'll be negative 3/16. I'll get that in a second. Over U squared. And then sine theta d theta is negative du. So there's du, and there's your negative that you're talking about. And how do we handle that? Split it up into two separate integrals, right? Or two separate pieces because you have a single denominator. So here's your negative 3/16 integral 1 over U squared, right? Which is the same as U to the negative 2. And then, hey, minus U squared over U squared is 1 du. We good? So now, antiderivative, negative, negative, and then this is going to be negative 1. Oh, antiderivative, no more integral sign. So antiderivative of this is what? Negative U to the negative 1 or negative 1 over U. Same thing, right? The antiderivative of 1 is U, right? Because we're integrating with respect to U. I think we're there. Well, we got to get it all back to x, right? All right. So what is U? Cosine theta. So what is 1 over cosine theta? Secant theta, right? So this turns into, I'm going to distribute this through here to here, positive 3/16 secant theta, and then positive 3/16 again. God dang it. I'm sorry. We've got people installing stuff in my house and they've got problems. I'll turn that off. Let me finish this at least. Plus C. All right. Let's do a quiz. How about that? Yes. Let's do a quiz. So I can buy myself some time here. All I want you to do now is finish this. All right? So yeah, on a separate piece of paper, what I want you to do is, you don't have to rewrite the whole problem. Let this be the first thing, and then take it the rest of the way back to x. Okay? Take it back to x. What are? Yeah, reciprocals, yeah. So when you put them, yeah, but because they're not multiplied, you can't just like make it all go away. Yeah. If you get it, just turn it in so I can determine where people are. Kelly, what's that look?
Do you want us to simplify this?
Hold on a second. You what?
Okay, so are you supposed to like solve this, or do you use 3/2 for this part?
Use that.
So it would be 2x over 3?
Yes,
Okay.
that is correct. That is correct. It's a little different than what we've done in the past, right?
You take this, since you could combine these two since multiplication, you can take this out from under as a
Thank you. All right, Matt.
Oh, I have to simplify this.
No, you don't need to simplify. Well, unless 3 over 48 is what, 16? Like you can reduce fractions, but you don't have to clean it up like algebraically. Get it? Feel good? All right, I'm giving you another like 2 minutes.
Do you have to do it like this?
Y'all ready?
Yeah, that's what I was thinking earlier.
All right, you got 30 seconds.
No. There's a flaw in the 3.
Make sure your name's on it. Thank you. Thank you. Thank you. Thank you, sir. All right.
Well, I don't know if we're right.
Anyone else? Last call? So what was the hardest part of finishing that out? Keeping track of numbers or what? Keeping track of the constants? Or no? What were y'all hung up on?
Maybe.
The reference triangle? Fractions, just fractions in general? Everybody turn in something? All right, so that's it for the trig substitution. I mean, you just got to get in there and get your hands dirty and try different problems, right? And that homework set, you know, I'm still working on the homework solutions on that. I've got probably 4 or 5 hours of video so far just for those homework problems. So make sure you do those, yeah. All right, but we need to start our last topic for integration, all right? And we've got about, 15, 16, 17 minutes. Yeah, that was the wrong page. That's supposed to be what? 326. The thing is, that's a PDF file. The file that came from, I lost. I don't know where it is. It's gone. So I can't really edit that easily, so I forgot about it. All right, so the last section, look, we've made it to the final way to integrate is section 6.3. It's called partial fractions. And this technique of integration requires that you know a lot of things that maybe you haven't seen in quite some time. So before we even get to partial fractions, I want to spend time just getting us ready for it, which is to remind you of Formula 17 in the table of formulas that says that if you've got 1 over u squared plus a squared in your integrand, that the antiderivative is 1 over a arctangent of u over a. That formula is very important. It's going to come up over and over and over. I told you that a long time ago, didn't I? Well, just a reminder. Now, we're going to look at some integrals right now that everyone in here, we should be able to handle these integrals. There should be no problems with these. And I'm going to actually go through each one of these. And I'm going to go quick, all right, because we should know how to do these. First one. If we have a constant like 2 divided by a linear expression like x minus 4, so a constant divided by a linear expression, we can handle this really easy if we make a substitution of u being the bottom, basic substitution. U would be equal to x minus 4. What's the derivative of that? Dx, right? 1 dx. And then we could rewrite the integral how? The 2 comes out. 2 integral 1 over u du. Antiderivative of 1 over u, natural log u plus a constant. And we just replace u with x minus 4, and we're done. And that would have worked for any time we ever saw a constant over a linear expression. We could just pop the constant out, choose that to be u. We might be off a little bit, but we would tweak it and things would work out. So we're in business if we see that, right? Okay, look at the next one. Another constant over a linear expression. So this is exactly the same as the one we just did, right? Our u here would be the 4 minus 5x. That would change one thing here, right? Our du would now be what? Negative 5 dx. So we would have to tweak that, right? Scale out the negative 5 by doing negative 1/5 on both sides. And then you'd plug back in, right? Wouldn't this be another natural log? Yes? Okay, so I'm not going to continue it. We okay with that? All right, let's look at the next one. If we have, I'm on number 3, a constant over a repeated linear factor. A constant over a repeated linear factor. We see something like this. So what do I mean by repeated linear factor? Well, this is a linear factor, right? 2x plus 1. If I square it, that means it's repeated. It's the same thing twice, multiplied. So the 2 is what makes it repeated. To do this problem, we would do exactly what we just did here. We would make the substitution that u is the linear factor. The derivative would be what? 2x, not 2x, 2 dx, right? We'd be off a little bit. We'd be off. Scale, and we could scale it and things would be scaled out and whatever. What would this turn into though? Forget the scaling. I mean, we know we'd have some scaling here. 1 over u squared, and that's u to the negative 2. So it wouldn't be a natural log when you antiderivative. It would just be power rule, wouldn't it? 1 over u squared, u to the negative 2. Yes? So we could do that. We'd be done. We're all happy. What about number 4? You have a linear expression repeated again. This time instead of squared, it would be what, cubed? So that again, u would be the linear factor. And you do your tweaking. Maybe you need to scale it out. Who knows? I mean, here you wouldn't. But this would turn into what? 1 over u cubed, and that's u to the negative 3. Use power rule, you're in business. So all of these we should be able to handle so far. How about 5? So number 5, that's what? It's formula 17, right? That's formula 17 exactly. You have x squared plus 9. We could use the formula. Let's go ahead and use the formula since it's our first example. The formula number 17 tells us that we need to identify what a is. What's a for us here? 3? So the formula says this should turn into 1/3 arctan of what? U over a, so x over 3. X is the variable, isn't it, instead of u? So the formula says if you have 1 over u squared plus a squared, that it should be 1 over a arctangent of u over a. Yes or no?
Yeah.
Okay. So look at, I'm going to, next to that, what did it say? If we ever have this, right? If we ever have a constant over a quadratic, where the quadratic is missing the x term, we can do this, right? Like, and it's being added together, right? We can do this. So as long as there's no x, what if there was an x term in there? That formula wouldn't work, would it? We'll deal with that, though. How about the next one? So the 16, 6. How do we deal with this? And I have how much time? 10 minutes. This should be perfect. I'm telling you right now that we should be able to do number 6. But we've never done one like 6. Let's see how we're going to do it. Integral 1 over x squared plus 2x plus 17. So what we are looking at right now is a constant over a quadratic, right? The quadratic has an x term, so we can't use formula 17 like we did in number 5. That x term throws things off, doesn't it? But it also says that we have that quadratic down there is irreducible. What does irreducible mean? It doesn't factor. If you try and factor x squared plus 2x plus 17, it will not factor. Right? That's not like x plus 2 times x plus 5 or something like that. It's irreducible. If you have an irreducible quadratic on the bottom and a number on the top, constant, we should be able to do something. Right? I haven't told you what, but here's what it is. Your favorite thing. Complete the square. All right. Yeah, you did that in college algebra for some reason or another. Oh, for this. This is why. Finally, we get to use it for something, right? So we're going to complete the square. So do you recall how the process of completing the square works? You take x squared plus 2x plus 17, right? And what we're trying to do, the ultimate goal of completing the square, is to get it to look like something squared plus a number. That's what completing the square does. It turns this into like something in parentheses squared plus a number. Before any of that. What does anyone remember from completing the square? The first condition that you have to have before you can even start. A 1, where? You have to have a 1 in front of x squared before you can even start. Which why on number 7, which I won't have time for, we're going to have to address that. But this first example, I put a 1 there for you. So you have a 1 there, right? Okay. Next step. No, it's okay if we don't remember, but just trying to see. What's that?
You move the 17 out of the equation.
Move the 17 out of the equation and leave a blank spot, something like that. Y'all remember this? Okay. All right, that's okay if you don't, because there's a problem with that. here's the problem with that. A lot of the times when you're taught completing the square, you have an equation. You do not have an equation. You are not allowed to work with both sides of this equation because it's not an equation. So I can't move things around, right? I can't? Do you agree? All right, so watch what I do. The second step after you make sure it's 1 is you look at the number in front of x, which is, in this case, 2. What do you do with that number? Anyone remember what you do with that number? You do half of that. You take half of that number. So this, you take the 2 right here, and you divide it by 2. And you just tell me what that is. It's 1, right? Now, what if this was negative 2? Then you go negative 2 over 2, which would be negative 1. You're always going to divide by 2, but you have to keep the sign of what's here. Okay, this right here is the first kind of magic number from completing the square. Then what you do is after that, you take that number, that answer, and you square it. And in this case, it's still 1, right? This is like your second magic number, so I'll put 2 stars on it. Does that ring a bell? Take that number, take half of it, square it, and then we do something with that? Okay. All right, now here's where things will be different from the way you probably learned it. If those of you, that might remember this, you were supposed to take that number and like add it on both sides of the equation. Again, no equation. So we're going to do something that's used in higher math that's a little bit better, is to realize that right here in front of the 17 is a 0. Do you agree that that's a 0 right there? If I take x squared plus 2x plus nothing plus 17, it's the exact same problem. Yes? All right. You agree with that, right? Now, I'm going to rewrite that 0 in a very clever manner. It's going to be this number right here, and then that number subtracted. So I'm going to add that 1, and then I'm subtract the 1. Do you agree that's 0? It's this one. This one's first, yes. No, not subtracted by this one. Just this one. Forget this one for a second. This one, act like it's not here, okay? This one's not here. Working with the second number only. But I'm trying to make a 0 out of this. The only way to make a 0 is to add it and subtract it. So if this had been a 2, I would add 2 minus 2. All right? You with me? But what's still there? Plus 17. Now, if you do this correctly, meaning if you take that number and divide it by 2 and then take that number and square it and then add and subtract it, if you do that correctly, the first 3 terms are a perfect square trinomial every single time. Without fail, it will always be a perfect square trinomial, which means what? This is something in parentheses times itself in parentheses. What is it? X plus 1 times x plus 1, isn't it? So I'm saying to you that will always, these first 3 will always turn into something squared. It'll be x, right, because it's x squared. And then, how do I get this number? How'd you get that was a 1? Because that's a 2?
Because the last one is 1.
Because the last one's, well, you know what? You don't even need to care. This is what the number will be, always. Okay? So this will be plus 1. Because that was plus 1, that'll be plus 1. So that's where that other one comes into play. So this right here is this, yes? What's still there? Minus 1 plus 17, which is plus 16. That's the correct way to complete the square when you don't have an equation. To realize a hidden 0 and then rewrite it and then make it happen. So the original problem now, right? The original problem is 1 over that irreducible quadratic actually turns into x plus 1 or x plus 1 quantity squared plus 16 dx. What can you do with that? A basic U substitution. What would your basic U substitution be?
Can't you also take 16 out?
Yeah.
Oh, no, you can't.
Can't, because it's added. Yeah. U is x plus 1, everyone. What's du? dx. How's the integral rewritten then? One over u squared plus 16 dx is du. How do you do that? It's number 5, isn't it? This is formula 17. That's how we handle things like this now. So you go, what? 1/4 arctangent of u over 4 plus c. Formula 17 gets you from here to here. But what's u? X plus 1. We're done. We'll get more practice with these, all right? But did I introduce you to anything new here other than the completing the square? Is there anything reminding you of completing the square? But there's no new technique of integration here, right? There's no, so far, this is just, what we're trying to do before we start this section, partial fractions, is we're trying to get kind of like a database of the things we can handle. We can handle constants over linear expressions, no problem. We can handle constants over quadratic expressions if there's not an x in there, or a middle term. We can handle a constant over a quadratic if there is a middle term, if it's irreducible, using completing the square. And then as we're going to see when we come back, that we can also handle linear expressions on top and irreducible quadratics on the bottom. And then we will be ready to start partial fractions. All right, well, I don't have any more time. Everyone kind of looks like they're here. Everyone turned in a quiz. I'll do attendance off quiz today. If you didn't put your name on your quiz, then you'll probably let me know. All right, so what are you going to do this weekend? 6.2. Everyone needs to come in here and have made an honest effort, honest attempt at completing the homework for 6.2, which is the trig integrals and the trig substitution. All right? Okay, have a great weekend. Yeah, enjoy some football, I guess. Excuse me, Ron.